I'm not sad for them. Okay, back on track to volcanoes now that I got the video set up. So today we're going to start off with volcanoes, and we should be able to go through this pretty quickly because we've gone over quite a few of the terms already for volcanoes, or at least the igneous terms. So we're not going to have to spend time worrying about the igneous terms. We can just concentrate on the volcanoes themselves. And so they start off, and you'll notice the top headline up here is Mount St. Helens. This was the last big eruption in the United States, the largest eruption in the largest historic eruption in North America. It was devastating for the mountain and for the entire region. It happened in 1980, so before I was born, obviously before y'all were born, and so we don't remember a lot of it. And actually, surprisingly, it's not like we were super technologically advanced in 1980. No one caught this on video, and it's always like frustrated me because they knew it was going to happen for like months, if not weeks. Well, weeks, if not months. But nobody at that moment had a video camera like trained on the mountain. And so when it erupted, we have a couple people that took pictures, and they've got some still shots, but no actual footage. The before and after the mountain is amazing. It lowered the peak of the mountain by 400 meters and essentially blew it away. It destroyed all the trees in a 400 square kilometer area. Mud flows traveled 29 kilometers down the Toutle River, and it ejected about 1 cubic kilometer of ash, more than 18 kilometers into the stratosphere. Very, very high. And so they have a picture. This is a before and after picture. And if you ever go to, there's like a Mount St. Helens, I don't know if you'd call it a museum or a science area, but they kind of go over the eruption and what happened. And they have this screen. I haven't seen this, but my wife's seen this. They have the screen that has this picture of the original mountain, this nice, beautiful peak. And then afterwards, like at the end, the screen like lifts up or moves to the left or whatever, and it's supposed to be like a window behind it where you can view Mount St. Helens today and kind of see that side by side in stark contrast. But the problem with Mount St. Helens is it's almost always foggy, and so you never really get to see that nice picture of Mount St. Helens versus the other one if you go to that visitor center. Almost like, has anybody ever been to San Francisco? I haven't been, but everybody wants to see the Golden Gate Bridge, and then you go, and like 90% of the time it's foggy, and you don't get to see like the entire bridge, just a part of it. So same thing with Alcatraz. You're like, where's Alcatraz? They're like, it's right there. You can't see it. It's in the fog. And so they got a couple pictures here. Here's some destroyed trees. This is like an entire forest that's leveled, and you can literally see the line where the shockwave died off enough to, it probably still killed the trees, but didn't knock them completely over, which is pretty cool. The next page, they go to Hawaii. So I'm going to go to my trusty videos real quick. And let's see. Let's just go through these. I was looking for one in particular, and I believe I found it here at the end, although it's not the one that I saw before. It's a little story about this guy who got some of the best pictures from Mount St. Helens. But these are all going to be pretty short and should give you an idea of kind of exactly what happened. So let's go through some of these. Oh, wait, hold on. My speaker's on back there. Promethean now.
Mount St. Helens erupted on May the 18th, 1980.
Hold on. Sorry. YouTube people, I will try to send y'all the links or put the links into Canvas, but sorry, you can't watch this. So look up, a man was hiking near Mount St. Helens when an eruption, and he captured is incredible. What he captured is incredible on YouTube, and you can watch the video along with us. For those of you following along at home, you can Google search Mount St. Helens initial explosion. That video was only like 1:45. And then Mount St. Helens eruption, May 18th, 1980, 720p HD is another short video. I don't know that we'll watch the whole thing. And then the last video I want to show y'all, which is the one I highly recommend, This brave student captured the Mount St. Helens blast, and it shows the story of a guy, and there might even be a longer one. It shows the story of a guy who got some of the best pictures of the eruption as they were happening. I did see a longer version, but I wasn't able to find it this morning. So you can look up those videos, and I will be back in just a second, or for you, like instantaneously, and we'll continue with the lectures. Real quick, while my internet crashes, let me pull it back up and see if I can show you all. Just real quick, the bulge that's kind of happening today at the crater. Let's see. Oh, are we doing this? Oh, my internet just dies. Oh, let's try Chrome. What the? Restart the computer. Let's see. Mount St. Helens bulge. That may be a risky search. Is that right? It says USGS on it. Hello? No, she's still online. Oh. No. Well, I haven't heard that she's coming back, and she's not in here today, so. All right. No problem. Bye. Let's see. Here we go. Is that right? No, none of that. I think that's it. Yeah, I think this is like a new little dome inside of the crater at Mount St. Helens that is pushing upward. They're talking about a glacier. I don't think that's a glacier. Anyways, I can't find it easily, so let's see, present day maybe. Mount St. Helens isn't where it should be. What does that mean? Light form in first. No, that's not. All right. Nah. They're calling that a glacier, so I don't know if it's what I was thinking. Anyways, they take lots of time-lapse pictures of this now after the eruption, and there's evidence that it's starting. It's not going to build back up and look like it was before without a lot of different eruptions, but there's evidence that it's starting to kind of get some more action happening underneath and build up some pressure underneath there. Not to like the eruption that we saw in 1980, but still. This 15 feet in line. Anyways, all right. Nice. Those are good videos. I don't know why my internet needs to stay up. See if it does. Now, so from a crazy, violent explosion that was Mount St. Helens, we go to the opposite, Kilauea, who's been just casually, like vacation style exploding, erupting since 1983. Literally my entire life, every single day on Kilauea, or Mount Kilauea, which is the main island of Hawaii. There's been an eruption going on, just nonstop, lava bubbling out and slowly making its way to the ocean. People casually standing just a couple feet away from a pile of lava that's flaming up and burning things. This is what you want if you're a scientist that wants to study volcanoes. Is you want a nice calm volcano that you can go and do things around. Maybe roast some marshmallows and have a nice drink and observe what's happening. So yeah, Hawaii has very, very different volcanoes than the western seaboard of the United States. So we'll talk about the difference between those, why they have such different eruptions, and what can kind of be learned from each of them. But the Hawaiian volcanoes are your typical quiet, non-explosive, non-violent eruptions, where usually when you have a oceanic plate subducting underneath continental plate, you get the volcanoes that are much more dangerous when they erupt. So, question, how are the eruptions of Mount St. Helens and Kilauea different? Mount St. Helens was extremely violent. It exploded all in one day, covered a huge, huge area, where Kilauea erupts very gently and has a very different lava composition. So Mount St. Helens is going to be more felsic, where Kilauea is going to be much more basaltic. So we go through terms. We all know what magma and lava is. Magma's beneath the surface, lava is above the surface, and they start to talk about what causes a volcano to be more violent or more tame, like the Kilauea one. And there's a lot of things that go into it. Your temperature. The composition is going to be really big. What kind of minerals you have inside the volcano, what it makes the lava like. Composition is greatly going to affect your viscosity. Where else do we use the term viscosity? Does anybody know? Viscosity. We don't see too much of it anymore because I don't think today's society really cares about this. But when I was younger, there were a lot of commercials about this because they were trying to sell you on a specific brand. Viscosity. Oil, motor oil for your engines. I don't know why, but you don't see like oil, Pennzoil, or what's the Pennzoil is the yellow one. Valvoline commercials or Mobil. They do have some Mobil One commercials, but yeah, oil viscosity. When you hear the term like 5W20 or 540, whatever, there's lots of different ones. That describes your viscosity at different temperatures inside your engine. And so you got to make sure you get the right viscosity for your engine. For your volcano, viscosity is going to depend on composition. What kind of minerals are inside? That's either going to make it a thick, not very flowing lava, or a nice, thin, runny lava that can just come out the surface and run down until it gets to the ocean and not really explode. And so the thicker, the more viscous the lava, the more explosive it's going to be, because it's not going to come out of the little cracks and holes like it needs to. The more runny or low viscosity is going to be a nice, calm, non-explosive volcano. The amount of dissolved gas, that's another contributing factor. And when they mean gas, they really a lot of times mean water. When we talk about volatiles in volcanic eruptions, usually that's water. And when you're talking about water at temperatures of magma and lava, it's boiled water. It is gaseous water. And so that does affect your volcano. And usually it's the opposite of what you would think. When we think lava and you add water to it, we think that it's going to like cool it down. It actually makes it, it kind of has the opposite effect that you would think water would inside of your magma or lava. So how to decrease magma viscosity and make it more flowing and less likely to erupt. You increase the temperature. Obviously, the hotter it is, the more melted it is, the easier it's going to be able to pass through the little cracks and holes at the surface and flow out. You also can decrease the silica content. Silica is going to be what you have in your granitic rocks, your felsic rocks. So if you have a more mafic rock or basaltic, which is high in iron, high in magnesium, low in silica content, that's going to be like your Hawaiian volcanoes that flows very, very easily. So rhyolitic magma or granitic magma has over 70% silica. Basaltic magma has roughly around 50% silica. So it's much, much more fluid and flows a lot more easily. And also if you add water, so we would think if you add water to a volcano, that's going to like cool it down, which is going to change the temperature, which is going to make it less resistant to flow. Adding water actually decreases your magma's viscosity and allows it to flow more often. Not more often, but better. So they go through a little chart here, composition of magmas and properties. We don't need to spend much time on this. Now, let's see. They're going to start with basaltic magma. Let's see where we're going. What time is it? We're not going to go too far in. I just wanted to show you all the videos today. We don't have a lot of time left, but we talk about basaltic magma, quiescent eruptions, explosive eruptions. We can get through this part, finish 7.2. So they're going to talk about your basaltic magma, which is generated by partial melting in the upper mantle. It usually happens at the oceanic crust and erupts as highly fluid lava, which is the kind of stuff that you have in Hawaii. Very, very fluid, just flows downhill, can flow for like miles and miles and miles, and then dump into the ocean and cool very quickly. At the continental crust, it collects at the crust mantle boundary, similar to the Mount St. Helens eruption. But the problem is when it comes up through the crust, it can add a lot of silica to it, and it can get less viscous and make a more eruptive, explosive volcano. Partial melting of the overlying continental crust generates dense, silica-rich magma, which is what's going to give you that explosion. So over your oceanic crust, you're going to have those less explosive volcanoes. At that oceanic continental boundary, you are going to get other melting of that continental crust, which is going to add to your silica content, which is going to make it more eruptive. So quiet, calm eruptions we call quiescent eruptions. They're triggered by additional magma to the near surface magma chamber. Inflation and fracture of the volcano summit happens, and your lava just basically like leaks out. That's similar to your ongoing eruption of Kilauea since 1983. Wonderful. I'm pretty sure, now I'm second guessing myself. Like, someone look up, is Kilauea on the main island?
It's on the Big Island.
It's on the Big Island. That's what I thought. All right. So yeah, because that's going to be the one that's most active because currently over that hot spot. So we talked about the hot spot a little bit in plate tectonics, and you'll see it in the lab once you get going on the lab. But that hot spot is what's feeding that Kilauea volcano. So they have a nice picture here and a little bit of caption. Not too bad. So your explosive eruptions are going to be the opposite. Your pressure decreases as your magma rises. Dissolved gas forms expanding bubbles, which is going to kind of help. Why does it say pressure decreases? I mean, yeah, your pressure is going to decrease because you don't have the overlying. Okay, here's what they're getting at. This decreased pressure is actually going to allow your temperature to lower. When you have higher pressures, you have higher temperatures. So as it rises towards the surface, not like right at the surface, but as it rises up to fill that magma chamber, you're going to decrease that pressure, which is going to bring your temperature down and make it more viscous. Your dissolved gas also forms expanding bubbles, which is going to help clog things up and keep it from flowing very easily. Your viscous magma expels fragmented lava and gas, buoyant plumes of material, which we call eruption columns. And then you get that rapid ejection of magma, which is your huge explosion that creates your very violent eruption of your volcano. So it reduces pressure in the magma chamber, causes further expansion, and then eruption. Wonderful. So they have their, I don't know, this is not Mount St. Helens because you have the water right up next to it. Eruptions of highly visible, they don't tell you where it's at, but not Mount St. Helens. What controls the viscosity of the magma and the quiescent or explosive eruption of volcanoes? So it's going to be temperature. The lower your temperature, the higher your viscosity, just like oil. Once your car gets heated up and you've been running it for a while, the oil flows real nicely. In the wintertime, where your temperature is very low, are you supposed to get in your car and just drive it immediately? No, it doesn't really matter too much down here because it doesn't get that cold, really. But if you live up north, you got to warm your car up before you start to drive it to work. And so you need to increase that temperature, which gives you a better viscosity, a lower viscosity. Increase your silica, which this is kind of like, you can't increase or decrease the silica of a volcano. What it has is what it has. It might increase itself as it melts other rocks, but it's not like anything that we can affect or usually happens. Usually the silica content is the silica content. So increased silica or more silica that you have, the more higher the viscosity is going to be, which is going to make it more eruptive. You can decrease your dissolved gases, and that will increase viscosity. So the more dissolved gas you have, the lower. No, wait. Yeah, the more dissolved gas you have, the lower the viscosity. So it'll be a nice, quiet eruption. And we'll leave off there. And we'll start tomorrow with materials extruded during an eruption and the different types they have. And we'll go through this pretty quickly. And pahoe hoe. Oh, and I'll leave you with this. Lava tubes. Empty tubes where lava used to be. From what I've heard, and we'll see how this goes, they'll have to find the right ones. But these could be our first moon bases. Living in lava tubes, because building on the moon's extremely dangerous because do you have a stinky sweater? I saw you sniff.
I thought it was a little bit. I think it was because of the rain.
Yeah. Living on the surface is really dangerous because the moon has no atmosphere and gets hit by even small meteors all the time. If we live in a tube, we don't have to dig it ourselves, and we'll be nice and protected. So we'll see. There are lava tubes on the moon.